All right, so we have the very first case for what to do when we're trying to solve this type of a differential equation. Let's look at the other two cases. D is equal to 0. When D is equal to 0, what we get is a repeated root, meaning that r squared minus ar plus b is going to be equal to r minus some value squared. All right? We have our two roots, but they're identical. And so if we go back to this equation, we put in r1 over here, r1 again over here, it doesn't help us out. It doesn't solve anything because all it gives us is just one value, one function. And we're just adding it up by multiplying it by two constants. They'll gather together. So there ought to be a second value somewhere over there. There ought to be a second function that will solve the differential equation. And the reason why we suspect this is because on the basis of things, it's a second order differential equation, so we expect there to be two solutions. But in the video in which we explain the theory, we'll see why it is that it really does make more sense than one would expect, that we would be looking for two distinct solutions. So over here, what we find out for now, through experimentation alone, when you take a differential equations course, you will be able to get a better sense of why this is the thing to guess. We can try y is equal to x times e to the r1x. All right, so all we're doing is we're taking the solution that we know, e to the r1x, and we're multiplying it by x. And we see what happens. So the derivative, just have to use the product rule, nothing special. When we take the derivative of x, this is that. When we take the derivative of the exponential, the r1 comes down, the x is untouched, and we are left with something which looks very familiar. It's the original y times r1. So that's going to be useful for us. We then take a second derivative of this, using the chain rule, we get r1 e to the r1x plus derivative of this thing over here. Okay, this is going to be r1 times e to the r1x plus, when we take the derivative of the exponential, a second r1 comes down, and we end up with something fairly long. All right, I don't know what to do with it just yet, but I can plug it in and I can see whether or not it's correct. I can check this particular value. So we're going to toss that into our equation, and we are going to get r1 e to the r1x over here, another one over there, that's two of them. So 2 times r1 e to the r1x plus r1 squared x e to the r1x. So this is y double prime plus a times y prime, which gives us this plus r1x e to the r1x plus b times y itself. And now we gather them up. We try to collect like terms and see what we have. So notice this one over here is the exponential times a constant, as is this over here, and that's it. The others, this one, and this one, have the exponential multiplied by x. So these two terms, let's gather them together. The other three terms, we'll gather those together. So the two terms over here are going to be 2r1 plus a times e to the r1x. The other three terms are going to be, well, I've got x e to the r1x in all of them. So I might as well factor that out. And I'm going to be left with r1 squared plus ar1 plus b times x e to the r1x. This right here, this is equal to 0, right? Because r1 is a solution to r squared. I've got a minus over there. That should be a plus. R squared plus ar plus b. So this one over here is going to give me a 0. Why would we look at this and still think that that might be a 0? Well, because our equation, let's shift this down a little bit, and let's fix this and pretend that it was a plus for the entire time. Our equation is a parabola whose vertex is at R1. So what I can do is I can, for example, I can take the derivative of this, and I will get 2 times R plus A is equal to 0. When is that going to happen? It's going to happen at the exact same spot. So we're going to get that this is equal to 0. A much nicer solution would be to simply complete the square. So you take the original r squared plus ar plus b, you know that it's a perfect square. Where is it going to have its vertex? It's going to have it at r1 is equal to negative a over 2. One way or another, the whole thing works out, and we get that this thing is equal to 0. So that's going to be our second solution. And so we get, we did not clear the boards, I apologize. We get y is equal to c1 times our expected solution from before plus c2 times this new equation, this new function, where we multiply by x. All right, so that's the second case. That's d is equal to 0. D is less than 0. That means we have 2 complex roots. So what we're going to get is that we can write the roots as some constant number or some real number plus or minus a real number times I. So we don't want to use a plus or minus b times I because we have a and b used already. We don't want to use x because we already have that. So we have to come up with some new letters. Sometimes that's a little bit difficult. Let's go with k plus or minus l times I. And just so people are clear with it, k and l are real numbers. Okay? So we have these 2 complex numbers, and what we get, and originally there's no obvious reason why this is going to be the case. We're going to have some constant times e to the kx times sine of l times x plus c2 times e to the kx times cos of l times x. Well, we can check this. We can run through, figure out y prime, y double prime. It'll only take us half an hour or so to plug it all in and go through the whole process, and we will get these are the solutions that we're looking for. This function over here, that one over there. Why that's the case requires us to go a little bit more deeply into the theory. So in the next video, what we're going to do is begin the idea of the theory behind everything over here. It might take us 1, might take us 2 videos, but we will get to why is it that you would expect these to be the solutions for a second order differential equation while everything up until now has been just the exponential function.